चलो, we are now doing the third problem. तो एक मेरे को प्रॉब्लम बता दो क्या बनी तुम लोगों की. पहले
मैम
ऑब्जेक्टिव बताओ.
ऑब्जेक्टिव फंक्शन को
मैक्सिमाइजेशन है या मिनिमाइजेशन है?
मैक्सिमाइज.
मैक्सिमाइज. So I'm calling it Z. Okay. तो क्या बना, ऑब्जेक्टिव फंक्शन क्या है?
मैम 200x प्लस 300y.
Okay, I'm writing it as x1 plus 300 x2. ठीक है. Why x1 x2 and not xy? Because ultimately we'll have to, when we are solving algebraically, and we'll be having more variables, so it will be x1 x2 xn. Okay, so I'm more comfortable with x1 and x2 subject to
Yes.
now the first constraint,
मैम 3x1 प्लस
which was
2x2.
with regard to the labor. Huh?
Yes मैम.
Okay, so 3x1 plus 2x2
is less or equal to 100.
less than or equal to 100. Then the second one,
मैम regarding fertilizer, then
हाँ,
2x1 plus 4x2 is less or equal to 120.
ठीक है. इसको तुम और सिंप्लीफाई भी कर सकते हो वैसे.
Yes ma'am. x1
Again,
plus 2x2
हाँ.
is less or equal to
So
60.
we can rewrite this constraint as x1 plus 2x2 less than or equal to 60. है ना? Is that right?
Yes ma'am.
ठीक है. And the third constraint,
Ma'am x1 plus x2 is less or equal to 45. I have made like this, that the land that is used for wheat and corn is limited, that is 45 acres.
yes. So x1 plus x2 less than or equal to 45. And x1 x2 more than or equal to, because this is actually the first constraint, the availability of, see, this was your labor. Okay, this is your fertilizer, and this is with regard to the availability of the land, because the first sentence itself says that the farmer owns 45 acres of land. So obviously he cannot grow more than he cannot grow on more than whatever is owned by him. So whatever amount, so basically here x1 is the amount of wheat grown and x2 is the amount of corn grown. So the total wheat and corn grown on the land cannot exceed 45 acres. So this becomes your third constraint. Okay, so this is your first constraint, this is your second constraint, and this is your third constraint. And these are your non-negativity restrictions. Okay, so now, as we discussed yesterday, to plot the inequalities, you will have the first quadrant only, right? So on this axis, we'll be plotting our x1, and on this axis, we'll be plotting our x2. Up now you have to do it simultaneously with me, okay? So, okay, I'll just plot the things here. Let's see the first constraint. What was it? 3x1 plus 2x2 less than or equal to 100. Okay, so what are the points that you are going to get? So when you put x1 and x2 as 100, what do you get? What are the 2 points? Huh? When x1 is 0, how much is x2?
50.
50.
When x1 is 0, x2 is 50. And when x2 is 0?
100 by 3.
100 by 3. So that is approximately how much?
33.3.
33.3. Okay. So, okay. Now, if I go here, let us, I will have my points like this. अभी इतने पे start करते हैं, ठीक है? And let's see whether we are able to plot it or not, right? On both. Are you also plotting?
Yes.
Okay. Now, what is the first point that we are going to plot is 0, 50, right? So 0, 50 is this point. And the next point is 33.30. So basically somewhere here, ठीक है ना, ये 35 हो गया, 33 is somewhere here. It's a rough plot, okay, of course you can use a graph paper in any case, right? So the line joining these 2 points will be something like this, right? This is my first constraint. Now, the inequality, the constraint had less than or equal to sign with it, right? And if I say, if I see here, then 0, 0 satisfies this constraint, okay? So the region is going to be this for the first constraint. This is going to be the inequality. Is that right? Now, the second is x1 plus 2x2, है ना? Less than or equal to 60. Now, what will be the 2 points? You have x1, x2, x1, 0, x2. So when x1 is 0, x2 is 30. And when x2 is 0, x1 is 60. So 0, 30 and 60, 0. Am I right or wrong?
I'm right.
Right. So 0, 30 is this point and 60, 0 is this point, right? So this is going to be my second constraint, right? This is second. Now again, does 0, 0 satisfy the constraints? Yes. So that means now my region is this. See, I'm now shading only the common region. Okay. Otherwise, this whole is also there in the feasible region. This region is also there for the second constraint. But since this region does not satisfy the first constraint, so the common region is only this, right? Now come to the third constraint. What is the third constraint? X1 plus X2, I'm writing it here now. X1 plus X2 less than or equal to 45. So ये तो आसान है ना? I mean, not that the earliers were difficult. So you have 0, 45 and 45, 0 as your points, right? So 45, 0 is somewhere here, 0, 45 and this point, है ना? So let us join these two. अब ये थोड़ा सा because मेरे लिए मुश्किल है. In case you are doing it in your notebook, I'm sorry. So yeah, so you have this whole region, right? But what is the common region? Common region, isn't it still this? Just check it up.
Yes, ma'am.
The common region that satisfies all the three constraints. This is your constraint number 3. Right? Though you have some region which is common to constraint number 2 and 3. You have some region which is common to constraint number 1 and 3. Right? But then since we need all the constraints to be satisfied simultaneously, so this is the region, right? So now what you can do is identify your, extreme points, which is this. I name it O, I name this A, I name this B, and I name this C. Right? These are this is the convex boundary of the convex polygon that you have got. Is that right?
Yes, ma'am.
Right. Now we'll write the coordinates for the 3 points. Okay. Now, what is the coordinate for O? That is 0, 0. What is the coordinate for A? What was this A? This point?
100 by 3 0.
100 by 3, 0.
Comma
Right? Huh. Now, I'll write for B also. And what is the coordinate for C first?
0 30.
0, 30. And what about this point B? Is
22.
lying at the intersection of first and the second constraint, right? So you can solve those two linear equations to get the points. It's an intersection point. So what are you getting?
I'm 20 20.
20, 20, 20. Right? So these are the four extreme points that we have got. Now, what was your objective function? Your objective function was 200x1 plus 300x2. So what we do is we compute the value of z for at each of these 4 points. So at 0, 0, the value of z is 0, right? What happens at A? How much is the value of z?
I'm 6666.6.
6,666.6, right? Is that right?
Yes,
What
ma'am.
about at B?
10,000.
10,000. And what about at C?
9,000.
9,000. So where do you get the maximum?
At B.
10,000 is the maximum. Okay. And it happens at B. Okay. So we'll say that the optimal solution, we write it like this, that the optimal solution is x1 equal to 20, x2 equal to 20, and maximum z is 10,000 units. Okay, so whatever your z was, whether it was the profit or, of course, it was the profit, right? And x1, x2 were the acres of land where wheat and corn were to be grown, right? So basically 20 acres, on 20 acres, we must grow wheat, and on 20 acres, we must grow corn. And the maximum profit that he can earn is 10,000 units, not beyond that. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Right? But sometimes what happens is, okay, now this is one way, where we can just identify the coordinates of the extreme points and then compute z. There is another way where we call is by the method of plotting the level curves. Okay. Just see, for example, question number 4, right? Uh, it says in terms of x and y. So let's write it like that only. We have to maximize x plus y subject to x plus y less than or equal to 6 and 3x minus y less than or equal to 9. Of course, x, y more than or equal to 0. Okay. Now, what we can do is, like, the way we plot the feasible region, that remains the same, right? So, like, okay. I think. Oh, I hope it's not very cumbersome. 0, 2, 4, 6, 8, 10. This is my x-axis, and this is going to be my y-axis. 2, 4, 6, 8, 10, right? Now, what are the 2 points for the first constraint? I think 6, 0, or 0, 6 and 6, 0. Is that right? For the
Yes,
first
ma'am.
constraint, will these be the 2 points or not?
Yes,
Yes,
ma'am.
ma'am.
Yeah. So you join them and you get the first constraint. And what is your feasible region? Of course, this one, right? What about the second constraint?
30.
3, 0. 3, 0 means
0.
somewhere here. And 0
0
minus.
minus 9.
So somewhere down the line. So you will get some line. Of course, I'm not interested at that region, but when you plot a line, so it will be something like this. इस तरह से बन जाएगा ना. I don't even have the space, and so I'm not. Does 0, 0 satisfy? Right. So that means this is your, because we are not interested in the negative part of the code. Otherwise, the x's run like this, right? So maybe to get a point, you might have to consider the negative x's also, but our feasible region, because we want x and y to be more than or equal to 0 also. So my feasible region will be restricted only to this and this. Is that okay? Now, as I was saying, one option is that I number the coordinates O, A, B, and C, and the way we have been doing, right? Now, as I was saying, the other is level curve, right? Now, what do you mean by level curves? What do we mean? Level curves means we will talk of, see, what is this objective function? It's again a straight line, x plus y equal to something, right? So it can take on some value, c1, x plus y equal to c2, and so on and so forth. So it's just that they will be a set of parallel lines because their slope is the same. It's only the intercepts that would change. So that means by giving different values to this objective function, we can get, a set of parallel lines in this case, right? So because we just have two variables, so it's a line. So supposing we have more than two variables, 3, 4, 5, and so on and so forth. So that's why we call them as level curves. Okay. So what we can do here is, instead of finding the coordinates, see, in these cases, whatever problems we are doing right now, probably because the number of constraints is less, so you are getting less number of extreme points. But say supposing you have more constraints, so obviously, like in this case also, you have four coordinates on which you need to sort of compute your z. But say supposing you have more constraints and therefore more coordinates for the extreme points, so unnecessarily you will be computing the values of z. Okay. So what we can do is, we can give a convenient value to this objective function. Okay. Say I say x plus y equal to 2, supposing. Okay. So the moment I say, okay, x plus y equal to 2, now I'm talking of the objective function, right? So if I just plot this straight line will pass through which points? 2, 0, this point, and 0, 2, right? So now I'm plotting it with a dotted line because this is my objective function that I am plotting. It is not a constraint, right? Now, what the theory says is that, like, say, supposing now you put x plus y equal to 4. So again, you will get another straight line. So what is happening is that you are getting a set of parallel lines here, right? Now, as you move this line in this direction, right, the value of z is increasing, right? And your objective was to maximize z. Okay. Now that means, though this line, when I say x plus y equal to 2, it lies in the feasible region, but it's not giving me a maximum value because I know that the maximum or the optimum value will lie at one of the extreme points only. Okay. So what you can do is just keep on moving this line. You just put a scale here and just keep on moving the scale till you are just at the boundary of the feasible region and you are able to get some point, where the scale just touches your feasible region at a point. Okay. So that point will be actually your optimal solution. Like in this case also, in the earlier problem, if you see, if you move the line in this direction, you will end up leaving the feasible region at this point, okay, which is 2020. Beyond that, if you just move beyond that, maybe the value of z will increase, but you will cross the feasible region. So no point. And if you remain inside, then there is a scope of improvement in the value of Z. Am I clear or not? Hmm?
Yes, ma'am.
Right. So, but like now, if you see this typical problem, if you see, if in your notebooks also, what do you observe when you are moving in this direction to reach uh, the feasible solution? What do you observe? क्या हो रहा है?
मैम वो बी और सी दोनों पे एंड हो रहा है तो दोनों पे मैक्सिमम आएगा।
सिर्फ बी और सी पे एंड हो रहा है या ये पूरी लाइन को
पूरी
टच
स्ट्रेट
कर रहा
लाइन,
है?
पूरी लाइन।
पूरी लाइन को टच कर रहा है. So in this case, what is happening is कि not just one point, any point lying on this line segment BC is giving you an optimal solution. And how many points can you think of between B and C?
Infinitely many.
Infinitely many. Okay. So this means if such a case happens, then this means that your problem has multiple solutions, not just one. You can pick up B, you can pick up C, or you can pick up any point between B and C. That is going to give an optimal solution. But what will happen is that the value of Z will not change. The maximum Z will remain the same, but the options to obtain that maximum Z can be many, infinitely many. Okay, so this situation we call as the case when the problem has multiple solutions. Okay, so you don't have a unique solution or just one value of x1 or x2 giving you some maximum Z. You have more than one option for x1 and x2 to give you a optimal Z. It could be maximization, it could be minimization also. That depends upon how your feasible region ends up with. Is this okay? Have you understood or not? बोलो जल्दी.
यस मैम।
Okay. Now, another thing that, I mean, this now I'm just trying to tell you how your problem can end up with. Okay. Like in the first case, in this problem, we got a unique solution. Only one choice of x1 and one choice of x2 that was giving us maximum Z. This is one situation, a unique solution, right? This is the second situation. Okay, maximum Z is not going to change, but you have multiple solutions to obtain that maximum Z. Okay, so this, in such a situation, we say that the given problem has multiple solutions. Okay, so this amounts to saying that you are giving the decision maker choice to choose any x1 or any x2, right? But you're telling him that his maximum profit is not going to change in that case. Okay, so this becomes the case for multiple solution. Now, sometimes what happens is that, when you are plotting a problem, I don't know which problem will end up like that, but sometimes what happens is that, your constraints, this is the third situation, we are talking of, when you have conflicting constraints, okay, in the sense that when you plot a region, feasible region, I'm just giving you one example, just hypothetical. Maybe this is one constraint that you get, and this is the feasible region for this. And this is the second constraint you get. They are not parallel lines, mind you. And the feasible region is this for it. Okay. Maybe, like this was some less than or equal to type constraint. This is more than or equal to type. So for this constraint, 0, 0 does not satisfy the constraint. Therefore, you get a thing like this, right? But for the other, And for this constraint, probably 0, 0 satisfies that constraint. Okay. So you get a situation like this. Now, what is happening? You only had two constraints and you do not get any feasible region. There is no feasible region for this. कोई आ ही नहीं रहा, common region ही नहीं है. So we say that there is no feasible region, and because there is no feasible region, therefore there is no feasible solution for this problem. So it's like the situation when you say when your system of equations are inconsistent. So in a similar manner, your system of inequalities are inconsistent in this case. Okay. So this becomes the case when the problem has no feasible solution. Is this clear? Then you might end up with a problem. I'm just giving you various options, you have to conclude there. Okay. You might end up with a problem in which, say, supposing like this is one constraint, right? And this is another constraint, right? And the feasible region is this whole region. Okay. So it's like 0, 0 basically does not meet the first constraint, but 0, 0 meets the second constraint. Okay. So the common region is this. Now, this feasible, when you end up with this kind of a feasible region, this is called as an, see, now I'm talking of two things. This is called as an unbounded feasible region. Okay. Now, for your objective function, let us see, what do you expect कि ऑब्जेक्टिव फंक्शन कैसा होगा और कैसे बिहेव करेगा इस रीजन में. कोई भी लाइन हो, कोई भी हो सकता है. जस्ट तुम्हारे दिमाग में देखते ही क्या आ रहा है ये बताओ पहले, देन आई विल एक्सप्लेन द थिंग्स. दिस इज द फीजिबल रीजन, राइट?
मैम उससे हो सकता है मिनिमाइज करना हो.
ओके, व्हाट इज द अदर ऑप्शन? दूसरा क्या हो सकता है? अगर मैक्सिमाइज करना हो तो क्या होगा?
मीन्स कि हम मतलब कुछ भी क्वांटिटी ले लें बढ़ती ही जाएगा फिर अनबाउंडेड अबव.
और कोई एनी अदर कमेंट apart from what she just said?
मैम इस केस में मे बी फिर मैक्सिमम एग्जिस्ट नहीं करेगा.
इन केस में मैक्सिमम एग्जिस्ट नहीं करेगा और
यस,
कुछ
ऑप्टिमल वैल्यूज नहीं आएंगी.
ऑप्टिमल वैल्यू नहीं आएगी, मतलब आप जो भी वैल्यू सोचोगे there would be some value of z greater than that.
यस.
Right. But as Swati said, if it is a minimization problem, then तो हो सकता है. सपोजिंग मिनिमाइजेशन का प्रॉब्लम है. See, when it's a minimization problem, that means your value of z has to decrease, till it reaches, maybe, मेरा objective function ऐसी कोई लाइन हो तो इस डायरेक्शन में तो ये बढ़ रहा है, फाइन, बट इस डायरेक्शन में तो ये कम हो रहा है ना. Shall I make it more clear? Say, supposing this is your objective function. I'm drawing it again. Okay, this is your z. So what is happening? As you move this z in this direction, the value of z is increasing. And since the feasible region is unbounded, that means the value of z will keep on increasing. You will not get a point anywhere where you'll get a maximum z, right? Such a case is called as an unbounded solution. Okay, but if it's a minimization problem, that means moving in this direction will reduce the value of z. So when you move it parallel to this, a stage will come when your objective function will reach this point, ye wala point, and beyond that you do not have a feasible region. That means minimum z will occur at this point, right? So that means in this case it has a unique solution. Okay, so what amounts to saying here is, or what needs to be seen here is, that the moment you end up with an unbounded feasible region, it does not always mean that the problem has an unbounded solution. Okay, even an unbounded feasible region can give you a solution, provided your problem is minimization type. Is this clear or not? Again, this is a very common problem which is asked, common question in interviews. If you have an unbounded feasible region, will the problem have an unbounded solution? No, not always. Depends upon the objective. Similarly, ये तो मैंने इस तरफ, that means in case you have a maximization problem, then it will have an unbounded solution, but may not happen for minimization. Is this clear?
Yes, ma'am.
So that means we have the cases where we have a unique solution. Okay. We have the cases where we have a multiple solution. We have the cases when there is no solution, and we have the cases when we have unbounded solution. So these are the 4 situations in which your problem may end up with. Okay, so then you have to, once you have solved the problem, then you have to judge. So unique solution means x1, x2, and z, all unique. Okay, multiple solution means z is unique. That means only one optimal value of z, but x1 and x2 can be infinitely many, right? No solution means solution does not exist. There is no value of x1, there is no value of x2 that satisfies all your constraints simultaneously. So that becomes the case of no solution. Similarly, unbounded solution means the value of z increases indefinitely. Okay, it is unbounded as x1 and x2 increase. So that becomes the case of unbounded solution. So these are the 4 things. And of course, in between somewhere, we have discussed what is called as an unbounded feasible region also. Okay. So as I said, unbounded feasible region does not always mean unbounded solution. It may or may not have a solution depending upon the kind of objective you have, whether you have to maximize it or minimize it. Is this clear?
Yes, ma'am.
Right. So